Great. Good morning, good middle of the day, good evening, depending on what part of the world you're in, and welcome everyone. I think this is the kickoff of the Munch and Learn Tech Talk series or forum. We hope that you'll all participate not only during this call, but in the various channels that are offered after the call. And so we to continue beyond this talk today, to register via HPE Dev Slack, also to go to the Munch and Learn channel, and we have a link for it there in the slide. And during the talk, we'd love, or after, for you to also have a little fun here. Let us know a little about what's happening with you. Maybe upload pictures of your munchies and start to chat, whatever you have on your mind, whatever topics you want to discuss. And then we have the slightly more serious channel, the Ezmeral Data Fabric channel that's listed there as well. And we hope you'll join that Slack channel. And that's for really after the event and as we go forward through the series to engage with the community. Let us hear what's happening with you, bring questions, bring ideas, bring discussions to that chat. But during this talk, if you have a comment or a question, please just put that in the chat window here in the Zoom call, and we'll take those questions at the end. We may have time for some during the event, and we'll have a few poll questions as we go forward. And so with that, let's start with our first talk of the series. This is Ted Dunning. Ted is CTO for Data Fabric here at HPE, and previously was CTO at MapR Technologies. And he's going to talk to us today about how and whether data infrastructure can actually change the way people work. If you're a developer, if you're a data scientist, day to day, does the data infrastructure you work on really make that much difference? If you work in IT, if you're an architect, how much impact does the data architecture have? And we're going to do that via several different specific use cases, but then dig below that. Ted will drop down into that to look at the implications of the technology and see really how it works, but most importantly, how it affects your work. So thank you all for coming. It's always a pleasure to me to be talking with technical people and developers, because these are people who actually build the world. This is where great ideas meet reality, sometimes head on, and then good things happen. And so with that, let's jump right in. Ted?
Well, howdy. You caught me just as I was taking another sip. It's an early Munch and Learn for us here in California. So what I'd like to do is talk today about Data Fabric and how various people I've seen use it, and in particular, what it is. And I'm going to start with these black background slides that are a bit markety, but we're going to dive in and you'll see the transition when we go to white background. These will be the tech talk sort of slides. And we're going to dig all the way down to how the data fabric is actually implemented. So today you're going to get a view from how people use it to how it works. Now, commonly what a data fabric is, well, let's change that. What it does, I think that's a better way to define something, is something that allows you to run the right applications, the right time, in the right place against the right data. Now, it doesn't do the running, it does the data side of that. And of course, data doesn't happen in a data center anymore. Well, it does, but it's not exclusive. You can't ignore the fact that things happen around the world, from medicine, finance, energy, science, all of it happens in many, many places. And I want to talk about three specific examples. They're very schematically presented here, but they give you an idea about what makes working with the data fabric different than working with your laptop. First example, this is a company that was founded back east, and they did video streaming. And at one point, a guy that I knew was running the engineering, and he needed some help. They needed some help. The way that the system works is pretty much like all video streaming. laptop or other computing device, consumer computing device, would connect to a server. The server was in a regional data center. And the question is it working correctly? Now, this team was very good at making streaming systems that worked well, but getting the telemetry back was causing them some issues, partly because there's a lot of things that can go wrong. Now, the easy thing to do is just throw things in a message stream, replicate the message stream back to your galactic headquarters, and do that from all the different regional data centers. And the key and interesting thing here is that if you do this at a fabric level, then from the application point of view, from the developer's point of view, you have a single data object that lives in many data centers. It can span your entire enterprise. Having the replication at the fabric level is actually really cool because the source, the application that's the source of the data, has no idea about all of the rest of the geography. And the analytical apps that are looking at the core stream really don't have an idea about how many data centers there are, except as represented in the data itself. They don't have to concern themselves with anything about the data transfer or the details of how the data gets into the stream. And so what we have here is a very, very strong separation of concerns between the source, the analytics, and the administration. It's not limited to media streaming. You can get any kind of data this way. It's used in 5G telecom, it's used in manufacturing systems, medical devices. All of these things generate data in a very distributed way, but can benefit from getting that telemetry back. And Data Fabric has these things built in, the Ezmeral Data Fabric in particular, and that makes it very, very easy. Here's a second example. We have a bunch of customers who are building autonomous vehicles. Now, to do that requires a huge amount of real-world data. That's because, of course, we want these cars to drive in the real world. And that means we need to get real cars on real roads in really different places and gather data from them. And this data acquisition happens with these companies by bringing the cars back to a regional, local field data acquisition system. It's relatively small as data centers go and kind of large as bread boxes go. It's kind of like a rack size thing. It holds 10 petabytes or so. But they copy the data directly into that system. That system then does bulk data transfers using the data fabric back to a core data center. Several of these companies are located in Germany, so it's back to there. And the key thing here, this looks a little bit like the first example, but the big difference here is that the data rates are very, very high. Multiple gigabytes per second per car. The cars are on the road nearly 24 hours a day. And so you get petabytes, tens of petabytes per day of new data across all these field stations. And so they run analytics in the field to reduce that, to find the data that they're interested in. And the data fabric moves the data back, moves metadata back. I'll show some details about how that works. But the ability to scale that distributed system is key here. Third example, and as I mentioned, these are pretty schematic. This one starts in a coffee shop. I don't usually buy coffee except for guests, but you might be buying tea. Your credit card will touch, swipe, I never like that word, touch a little credit card terminal. That'll send data back to a core system, and eventually that'll get backed up. A lot of financial companies actually use the Ezmeral Data Fabric once they get back to the core centers, and some for regional centers as well. But here, one of the issues is that you have to build models, like fraud models. And the myth here is that the data scientist builds the model. this is actually kind of silly because it's not just one data scientist. A lot of these companies have thousands of data scientists and they build thousands or more models. And the data is prodigiously large, tens of petabytes. And so you can't give each person a copy of it. And you can't even produce a lot of development duplicates for groups of systems. So you wind up with these data scientists running against the production data system. And when you have thousands of people doing relatively ad hoc things on mission important, if not mission critical systems, multi-tenancy is the key characteristic for success there. Yeah, the transport's good. Yeah, the scale is good. That's from the first two examples. But in this case, the multi-tenancy is the key property. So here we go. We've got three key properties that we're going to talk about, how it actually works. The planet scale, spanning geographical scale, the byte size scale and number of petabytes per second that you can read, and the ability to share safely. Now, the data fabric is going to make all that happen, but let's dig in here. First, a little bit of history. A lot of this technology came out of traditional computing. And anybody who remembers far enough back, and there's fewer and fewer people who do, remember that the idea of file systems was once upon a time a big, big deal. Once upon a time, you actually were allocated disk in terms of sectors. You were given those sectors. That's where you put your data in. Very, very low level of abstraction and so on. Multics and Unix and Linux and POSIX have all introduced this idea and made the idea of directories and files and block devices and so on ubiquitous. That was a big deal. And that gave us a lot of compatibility and functionality, ubiquitous now in operating systems. But it limited the scale typically to a single machine. 10 years ago or so, 13 years ago, Hadoop was built as a clone of the Google file system to get more scalability, but they traded away essentially all of that compatibility. And you can insert S3 as the same sort of system, giving up functionality to get scalability. And back in the day, we started MapR as a way to reintroduce that compatibility and functionality while further increasing the scalability. We ultimately added things like tables and streams and rebranded along the way. And then this company was acquired by HPE, and that technology forms the core of the HPE Ezmeral Data Fabric. So that's how we got to here. These provide new kinds of tools that do new things. And we've actually got a book coming out. When is it, Ellen?
So yeah, let me just say a few words about that, what this has to do with your talk. This is a short O'Reilly book. It's supposed to be published today, and it will be made available for free as an ebook through HPE's website. They are publishing it on the website today, so I don't have a link for you yet. But Ted and I wrote this book together, AI and Analytics at Scale, Lessons from Real-World Production Systems. And part of what we talk about in the book is that we've realized over the years that people are accepting trade-offs between the sense of scalability and reliability, trade-offs in the sense of being able to really put multiple things on the same system. Ted earlier had a slide that showed three use cases. The first one was talking about geo-distributed telemetry. The second one with people building autonomous cars and doing that from edge and huge scale. The third one, I think, was a financial use case and talking about multi-tenancy. But the idea is some of those are using advanced analytics and various kinds of data science. Others are actually running AI and machine learning. And these are drawn from real customers who are using this technology. And what we've seen is that they can easily run these systems, these different kinds of applications, very large systems together on the same system, on the same platform, and addressing the same data. And when you have that kind of unified data infrastructure, it breaks apart some of these trade-offs. We've been surprised to find that people who aren't doing this feel that they have, for example, to run AI on a completely separate system from analytics. And that breaks apart the opportunities for collaboration. It breaks apart how people look at data altogether. It certainly costs more, it's harder to manage, and so forth. And so that's why we took this topic for the book. And we go through in the book a huge number of, well, not huge, but a large number of actual real world use cases. These were all drawn from our customers, things that we've seen, various problems that they're solving. And then we talk about how they've done it, but also what the idea of having a unified data infrastructure that works across all of this data and all these different applications together. So we, Didier, we'll have a way to make that, or through our Slack channels, the link available as soon as that's up, probably in about a week or two. But keep those ideas in mind. That ask yourself, as Ted goes forward now through the rest of the talk, are you possibly accepting some trade-offs? If your organization is accepting some trade-offs that aren't really necessary, a different way to put that is that life can be easier. So with that thought in mind, Ted, jump into the more technical part of the talk.
Yeah, and Ellen, I can't remember do you remember how many case studies we have in this book? It was
I should know that. I think 20.
20 or something, yeah.
Yeah.
Now, this book is not super technical.
No.
You can actually give it to a manager without getting in trouble. But it's also not super technical either. It doesn't go too deep into it. It doesn't, but it's not particularly marketing fluff either. It's talking about real people doing real things. So anyway, off we go. Here's one recent example. I don't remember if we got it into the book, but it works. It illustrates some of the details about how a system can build up over time into something that's very complex, and how we can simplify that with Data Fabric. And it's nice because I have all the details right here at my fingertips. So this company that works in financials, they get data from a lot of banks. And obviously the way that worked originally was probably FTP, but now it's web oriented. And so they would stand up servers, each one with local disks, and the banks would come in, there'd be load balancing, and they'd store the data on a local disk. That's limited. So they added an NFS appliance. They would copy from the local disk to the NFS appliance, and then they would run a masking process on that data. Then they would do some data extraction, but that limited the scale. So they added HDFS, as was fashionable at one point, and they could run analytics using Hive, but they wanted to do machine learning, and a lot of the machine learning that they wanted to do was limited in terms of the APIs. It didn't necessarily speak HDFS, so they copied it out to S3, where they were running Spark and other machine learning systems. They also copied it out to a cold object store for lower cost storage. Now, if you look at it, they have an ungodly number of systems to maintain. There are 4 different storage systems. There are at least 4 different execution environments. And if you look at just the copy operations, from the original to just the copies, it doesn't simplify very much, meaning a majority of the efforts that they have are just scheduling, verifying, and doing these copies. It's really much easier if you don't do that. If the ingestion can work with the data fabric and drop the data into a volume, then you can have ingestion that runs on any node that's in a secure network. And you can have as many or as few of them as you like, and it's easy to scale them and easy to do that. The masking and extraction, of course, are done on secure data. And then people put it into a working directory where the analytics and the machine learning can all access the same data. And by the way, somebody's asking here about Ceph and Rook on this same sort of idea. We do see a little bit of adoption of Ceph and Rook in the field, but Ceph is complicated to run, and it really doesn't scale as large as the systems that we're talking about. Petabytes is considered large in those systems. Tens of petabytes is considered world-class, and that isn't that big, really. A lot of people go well beyond that. By the way, the data fabric can also handle the cold data problem as well. So instead of a huge number of these gray rectangles representing different systems to maintain, we have one that works across all of the ways of dealing with data that we need. From the standpoint of people building function, they can think of it very, very simply now. They don't have to think about where their computation runs, and they only have to think a little bit about where the data is. They build these, what we call volumes. They look like directories. I'll show you one later. They have to manage the security on roughly 3 things, and the complexity and placement and things like that on just a few things. They don't have to worry either about the computation location nor about which machine the data is actually on. They separate the concerns. They worry about function. The IT team, on the other hand, has a comparable but at right angles view of things. They maintain one storage system, the data fabric. It can scale to multiple data centers as necessary, and typically one scalable computation environment, often Kubernetes. This vastly simplifies the IT platform engineering because they think about data fabric and stuff. And the function, the application teams, the DevOps teams worry about the details of that stuff and the details of what they store in the data fabric. So that's emblematic of that, of how analytics is simplified. That book we're publishing today is about analytics and AI together. And AI, machine learning, I'm old-fashioned, I call it machine learning more, is surprisingly not about the machine learning that much. It's about the logistics. I have a ruder word that I usually use for the logistics, starts with a B and ends with a T, not supposed to say it in public. But anyway, the idea here is that instead of writing code, you learn it. We call the code a model. And after you learn it by a process called training that you apply to data, you deploy the model. And then you apply more data, and world domination and profit ensue, of course. Now, if we drop all that into a black box, it turns out that that little black box, even though it's the fashionable part, the part that we all wear black, is a small fraction of the total effort to make this have real value. There's a diagram that I steal from a Google paper all the time that talks about the hidden technical debt. And most of the effort here is in these other parts. And I think that there's huge value in these boring bits because they can drown out the cool part, the fashionable part, the machine learning part, or even the interesting analytics. If the boring stuff, if data transfers and copies and managing data are 90% of the work, and managing models and putting them right places and making sure the deployment runs and monitoring and so on, if you do that boring part just a little bit worse, your total time budget will be more consumed by the boring part and your clever bits will be smaller. If you do as I mentioned, the boring part is 10% smaller, then your 10% of your budget gets squeezed down to 1% of your budget. That's
so
bad.
I just want to jump in with a comment there. This is true of machine learning. It's actually true of other things as well. These logistics and the the weight of the effort of the logistical part of handling data and handling the applications is still a big part of the work, whether the little bit in there is AI or whether it's analytics or some more traditional way of looking at data. I think that with AI and analytics, AI and machine learning, it's amplified. That problem is amplified. But just a different issue here is there's increasing interest in people doing AI and analytics. I think a different takeaway from your slider slide here showing how you can squish down the effort if you're not careful, is that the people who are actually involved in producing a successful AI project go way beyond the people who have the very specialized knowledge to be working with algorithms and actually building and training the model. And so more and more people are developing those data skills. They're becoming data engineers. They're becoming active parts of a machine learning or an AI team. And they're doing that with fairly traditional skills as a developer and just adding on a bit of extra skill in this particular way of working with and looking with data. So the things that you're talking about here extend way beyond the people who are the very specialized AI experts, right?
Absolutely. And I think that this democratization, to put a fancy word on it, is going to accelerate. I think that, well, back in the 90s, in fact, there's somebody I worked with from the 90s on this call, building websites and servers and stuff was considered arcane knowledge. Only a few people could do it. It was amazing. It's now totally boring. Everybody can do it, at least at a very basic level. And shortly, in a few years, everybody who does any kind of back-end or data type stuff is going to be able to build simple machine learning systems. They may not build the most amazing fancy ones. They may not build autonomous vehicles, but they're going to see that as just another tool in their toolkit. And I think that data is going to go the same way. It's going to become ubiquitous. And so it's really important that we focus on these boring bits precisely because they will eat the clever bits. They will eat the valuable parts. And something I like to say, and I just saw that Camille Fournier, who's fairly prominent out there on the Twitter sphere because she's built some very good systems, says a variant on that is systems aren't ready for business until they're properly boring. She says, make boring plans that keep the exciting part to yourself. The consumers should not have that excitement. And so what we're talking about here is a change in the fundamental architecture of systems. Actually, Ellen, this is kind of an interesting thing. I've got lots of discs on here. We have some questions for the audience, don't we?
We do. I was going to ask if we could start with that first poll question. Audience, if you will just jump in and make a selection here. The first one is just for us to get a sense of the size, the scale of data that you're often working with in your system. So we're just going to take a few seconds, go ahead and answer. We're going to have a report at the end of all this. I think we have 3 or 4 poll questions throughout the talk, and we will share the results of what we see or some kind of thought about that via the Slack channels going forward after we get the full report from the meeting. But we'll give you a few more seconds here. It's also
really kind of exciting. It's like real-time data.
Yes, and grab their, take a bite, take a picture of their munchie, upload it to the Slack channel, make the rest of us jealous if your munchie is better than ours.
It is, I'm sure.
By the way, this series was originally going to be called Munch and Learn, and then we thought about the fact that we're all in various parts of our day. Sorry, Lunch and Learn, and so we changed it to a munch.
Yeah, I think we see a pattern evolving.
Yeah.
That more people have smaller data than have bigger data, but a fair number of people have truly enormous data. And
one thing that is important about the system and the technical underpinnings that you're about to describe is that it should be able to handle fairly large working with really small amounts of data, this is probably not the best system for you. But for people who are working with large scale data, it should handle what you have now. Systems grow. I mean, naturally with the project you have, new projects, you may start using a new data source and just suddenly jump up to an entirely different scale. It's important to have a system that can take that kind of change, not just scale, but scalability, without having to re-architect, without people on your IT team want to come and hit you on the head. And so having a system that deals with scalability as well as the current scale that you have is very important.
Yeah, those people with 100 petabytes didn't start there. They started with less than 100 terabytes and moved up bit by bit, byte by byte, petabyte by petabyte to get to those large scales.
Okay,
And
I
so,
think
yeah,
we'll close the poll, and if you want to go ahead and jump in,
that's,
Ted.
yeah. So I'm going to close that little window. So traditionally, systems in business are built using block storage. And the idea then is that we fashion a bunch of disks in a shared resource together. We might do that using direct attached storage, using something like the Linux Volume Manager, or we might use something like a Nimblebox to glue those together as a virtual block device. And each machine would have its own operating system and would have its own file system. And objects obviously do not span, and objects are located on particular machines. And what we're talking about here today, diagrammatically, is pretty simple. We're talking about raising that dashed line, which is that abstraction barrier of the file system, up one level. We're talking about making the file system be fully distributed. And that allows us to hide the location of computation, and it lets us hide the location of the data. So let's move on to talk about what it takes, what it looks like in the hardware sense to build these systems. If you build a rack, now it doesn't have to be a full-scale rack. On my desk, I have a laptop, a monitor, 2 Raspberry Pis, and 3 Intel NUCs. The Intel NUCs are a data fabric cluster. The Raspberry Pis are not, but they can access the data fabric. And so it doesn't have to be a full rack scale system. It can be relatively small, kind of the size that'll just a bit fit into your pocket if you've got big pockets. But typically it is 5 or more servers to get lots of redundancy. These will fit in with some tenant or application servers, and together you'll get computation and storage. You can scale it though by simply adding more racks or more storage machines. As you move to more racks, the storage, the data fabric nodes, the data fabric cluster is usually decreased in size on each rack because you'd like to spread this data across as many fault domains as possible. And as it gets very large, the little red boxes become bigger boxes. Typically, you start using very dense systems. One example is the HPE 4510, which has 60 disk drives in it. That's a lot of storage in each one. And with these dozen racks that I'm showing here, we get about a 24 petabyte usable system. That includes all redundancy for multiple storage to put the data on multiple racks and so on, and all operating system level headroom and so on. So that's how you scale it, really just by adding hardware. And that's a key property there that you need in these large systems, is the ability to grow from small, from 3 NUCs on my desk to large production systems. Now, geodistribution happens in these systems because we have a couple of capabilities. In the telemetry example that I used earlier, this is a little bit more detailed view of it. There are data streams, message streams built into the file system that underpins the data fabric. These are primitive objects, just like files or directories. They live in directories just like files do, but they have a different kind of API for the first case. And that expresses the byte life cycle differently. In a file, you have an array of bytes, and they live until you delete the file. With a message stream, you put in records instead of individual bytes, and they kind of evaporate over time when a time to live has passed. So it's a different life cycle, but it's just a bag of bytes in a similar sense to a file with slightly different organization and life cycle. But with the data fabric that we've built, there's also the ability to have a message stream replicate to another message stream. The only constraint is that a topic in the message stream should have one origin. They can all replicate, however, to a single message stream. So in each local data center, you have a very simple structure. You have data that writes to that as if that were the entire world. The replication then moves it to the global one, and typically you name data topics with data center dot machine name dot metric name, so that they're all unique once they get to the central point. And that means that you can read all this data, or you can read wildcards that'll update and so on, and you can process them very, very simply. I like to say you can see the entire world in a drop of data. So that's one capability. Another capability is the ability to move these entire volumes, which again look like directories, I'll show them in a little bit, at one time. You can also use these to, go ahead, Ellen.
Yeah, so just as you're moving in here, the point here, there's several points here, but the big point is that as you move data with a system like this, the system, the infrastructure is letting you handle these things at a platform level. You're not having to build them all in at the application level. Is very much, I think, the example that you just showed. But it's not just, as you're about to say, with data streams where you have direct stream replication, you have direct bidirectional multi-master table replication. You also can actually mirror data, and I think that's what you're about to show. Let's take a moment here for next, I think our question is about whether people work across multiple data centers, or I have the poll questions out of order, but could we take a quick poll, Ted, and find out for the audience, are they working all in one place? So audience, if you'd please weigh in here, and I think here we can actually have multiple answers, if I recall, because maybe more than one situation applies.
Well, this is interesting. The previous question, we kind of had a monotonic decreasing in the number of people with large scale, but here, at least in early returns, we cannot yet project a winner. Majority of people seem to have multiple data centers.
And I'll just say, for the phrasing of that first question, you may work in a single data center and not worry about the rest. We're really saying, do you focus on a single data center? Do you have multiple data centers? Do your data centers include edge, include a field and transfer back to a core? And that core, by the way, can be on with the kinds of situations we're talking about. It can be on premises, it can be in cloud, it can be a hybrid. You can have a system that cloud, hybrid, and multiple different centers in each of those locations.
Yeah, that was very interesting. It wasn't that long ago when people said, oh, getting a second data center is not a good strategy for increasing reliability. It'll just decrease it because now you have 2 points of failure. Clearly, a lot of people don't agree with that anymore. And I certainly don't agree with it anymore. It used to be hard to do, but it's become much, much easier. And by the way, as we go along, I'd like to remind people that I'm happy to answer questions pretty much as we go. If it gets too intense on the questions, I will delay that until later, but happy to kind of keep a side eye open for those.
Okay, so it looks like, especially from the results of this poll, some of the things that you're about to explain in terms of how this can be handled very efficiently at a platform level will apply to a lot of people in here.
Yeah.
So I think we can close that poll, and thank you very much for responding. And Ted, if you want to continue.
Yeah. So what I want to do is provide some of the details of the way these automotive companies handle those large volumes of data. As I mentioned, at the edge, they have a full-fledged data fabric cluster there. They do the ingestion into a series of time-stamped volumes. They do this because actually deletion of data is a time-consuming task because you have to traverse the entire file system if you delete it in a traditional way. But if you put it in a volume, you can delete the entire volume at once. So it's actually nice to be able to have a separate volume for each timestamp. Every time they ingest data from a car, they also record data in a table. I mentioned the data fabric has message streams. It also has a NoSQL database built into it so that you can create a table just as easily as you create a file. So as they ingest it, they put metadata. I just acquired this raw data file and it's in this place, and it was part of this test process, and so on. As they extract from that raw data to find just the test that they're interested in, I want this corner on a rainy day turning left, they will store the metadata for the extracted data, and all of the extraction and analysis code is stored in a code volume. Now this happens at each edge cluster. In the core, on the other hand, they have kind of a simpler, at least conceptually, system. They have the metadata table, they have the mirror volume where all the data sits. People look at it from special applications and they run big machine learning algorithms against it. They do extraction, they do simulation, they do ad hoc queries against it. They run analytics about how much data they've processed, how many times they've done learning, and so on. Now, notably, they've got the code volume here, and the edge and the core work together. The metadata is replicated in near real time by a magical link, just like the message streams are. The transfer volume, the mirrored volume, is moved by a process called mirroring, which takes a moment in time, does a snapshot, and then transfers just the changed file data. The code that's run on the edge is mirrored out to the edge in a reverse process. We can control this mirroring at the volume level. And interestingly enough, and I think I'm going to show that right now, you can actually use the exact same file name for data that's at the edge or that's in the core. So here I've got a terminal which is logged into my little itsy bitsy data fabric. And I can go to a directory. And the name of it here talks first about the cluster, mapr C0. C0 is the name of the cluster. And then it has my home directory there. If I do a listing on that, of course, that works just like you would expect things. You can see directories, files, more directories, and this thing is a table. And that table can have a replication pattern expressed. And this directory that I'm in, my home directory, is a volume. And as it turns out, foo is also a volume. From this point of view, you can't tell that it's not just a directory. And that's kind of cool. That means people don't have to worry about it. Now, if I go back to my laptop here, I can go to exactly the same path name and see exactly the same data. I don't have permission on everything. See that T1, I can't see tables through an NFS link or through remote access like that, but I get exactly the same path name, and that works over geographic scales. And so one of the common things that people do is they're looking at the metadata of data that has been processed, acquired, and is being mirrored or has been mirrored back to the core. They look at the core data often, but sometimes a test doesn't go as expected and they want to access the raw data, and they can do that directly from Windows machines or Linux machines in the core facility itself. And they can then mirror new code out there, reanalyze the data, or they can just extract it directly if they just want to read that data one more time. This gives a simplicity to a really complicated thing. Now, I've talked about volumes over and over again. I draw them as these triangles. I often draw directories as little ovals. They fit into the hierarchy just like directories. As we saw, my home directory had a volume in it and it had subdirectories in there. So I'm going to speed it up a little bit. These volumes can also have shadows with different properties. One is that you would have normal triplication of data, and then on the shadow you might have erasure coding. The data fabric handles that different form transparently, and so it goes either way. This is really helpful when you want to optimize data space. And let's talk a little bit about the internal representation as well. Data is broken into pieces. You can actually ask the file system how these pieces are done for any particular file. Typically, these are hundreds of megabytes in size. They can be as large as gigabytes, the chunks, or as small as individual megabytes. That's useful for increasing or decreasing the parallelism of data access. These are grouped internally by the file system. Each chunk is stored on a single machine, and then that machine breaks them up into 8 kilobyte blocks grouped into super blocks of 64K. And then those are stored in an internal data structure called a container. And that's where the magic really happens. That's where the replication or the erasure coding happens. The containers are the unit of transactions in this data fabric inside this file system. There's a replication chain for each one. Each container is limited to about 32 gigabytes in size. It contains pieces of files, directories, tables, and streams. And as I said, it's replicated across machines. It may be simple replication like this or fancier stuff. But one of the cool things is that the replication patterns are semi-randomized. And the exciting thing about that is that this randomization, and it's semi-randomization because it's adjusted slightly in order to get better resiliency. If, for instance, we lost this upper middle machine, the upper left, the upper right would have the yellow data, and the lower left and the upper right would have the white data. And obviously, if we have thousands and millions of these containers out there, then the statistical properties become simpler, although much harder to draw. And what happens then is that if you lose a machine or if you lose a disk, the entire cluster can participate in restoring that data. That gives us some really good scalability and resiliency in this system. It's all defined in B trees, interestingly enough. There's a Linux file system called BTRFS that does something similar on a small scale, on a single machine file system. But this is very, very useful. Files are actually B trees indexed by offset. Directories are B trees indexed by the hash of the file name. Tables are B trees indexed by the key that takes us to a tablet, which is a B tree, which takes us to partitions, which are B trees, and each one of those have segments, which are the write-ahead logs. And so all of this can be stored in the same technology, the same container structure. Containers themselves are B trees that devolve into the things inside the B trees. Now, as we saw, and this is largely just for the posterity's sake, when you look at it later, you see things as if it were normal. You see it from the Hadoop point of view as a file system with path names, from the POSIX point of view like this, with the same path names. Tables,
So,
streams, files all share that. Yeah, Ellen.
so jumping in, I sort of challenge people and us at the beginning to think about the things that you're describing, but literally, what difference would that make? If you're working on this system and you go to work tomorrow, does it matter? And I think part of the interesting thing about this data infrastructure is if it's doing its job, it becomes largely invisible. The point is a lot is being handled in kind of an automated way at the system level, at the platform level. And so a lot of things that you would have to do day to day if you're the developer drop away. You showed a workflow at the beginning, and you showed how that workflow became very simplified, both in terms of how many different systems there were, but also some of the steps in the workflow actually become not necessary. There are copying steps that aren't there anymore. A different way of looking at it is from the application point of view, is the application is, because of what you just described in this global namespace, you're referring to data by the same path name. And so different applications are able to access data by the same path name, regardless of where that application is running. So you actually can do that remote access to data in addition to doing the data motion. That can change some things that you're doing. You don't always have to move data in order to use it, but you can easily move it if you need to. What are some of the other implications that actually have a different feel to how people do things?
Well, it's more boring, at least in terms of having to deal with infrastructural issues if you're doing application stuff. But also, it's more boring in the sense that infrastructure maintainers don't have to deal with application details. You can have your excitement, you can do your exciting application, or you can work on big infrastructure without imposing the excitement that you have in your particular field on other people. And that, Ellen, as you were pointing it out, is exactly the core important feature of this entire system, is that it becomes boring in the right places. You don't have to worry about the mechanics of how LS works if you're just going to use it. You don't have to worry about volumes if all you're doing is writing a single application on a single location. And you don't have to worry about the applications if all you want to do is think about the data motion from data center to data center.
So, Diddy, I think we have time. We have a last poll or 2 poll questions left. And then if there's time, I have a general question for the audience. You would jump in and respond to this one.
Yeah, and this one is about have you been adopting these container technologies, and in particular Kubernetes, for managing workloads? And this one's a real horse race here. And interestingly enough, containers are holding their own against VMs. I think that if we were to say how many programs run in VMs versus containers, it would still be a win for VMs, but I think that an awful lot of people use both, and it looks like the adoption is very, very high.
And it's only partially displaying on my screen, but Ted, do you need to quickly say, I mean, we have about 12 seconds, but any information about the oscillation overthruster there? Question.
Yes, I should mention that.
But you have very little time, yeah.
A slimy thing to stick into a poll like this. Oscillation overthrusters, of course, everybody cool knows about the movie Buckaroo Banzai, except for the people who don't. But it was a great movie, and the oscillation overthruster was the key MacGuffin in the movie, been used again and again and again. It was the flux capacitor later in Back to the Future. It became key parts of various Star Trek movies. So it's now well, there we go.
There's somebody
who mentions
So,
across the eighth
so
dimension for the
we're
bin.
really testing the audience to say how many people in the audience have odd taste in sort of cult science fiction movies. So I think
And
we'll
unfortunately, large number of them clearly.
clearly do. So
You monkey
we'll
boy.
close that poll question because Didier, we're kind of at the end of the hour. Do we still have another poll question?
We have a session poll at the end. I'll bring it.
Yes, okay. And then I just want to throw this question out in general to the audience, and we don't have a official poll set up for it, but I would love to hear back from you either in the chat now or later. Some of the things that we were proposing and some of the things you'll see as you get a copy of the book and look at it is this idea of running multiple types of systems together, AI and analytics together on the same system. The idea of that kind of multi-tenancy, not sharing because, gee, I can't get my own cluster, but you don't want to have your own cluster. You want to be able to share these systems and collaborate and make it easier, make IT happier and as you go forward. I want to know, do those approaches resonate? Do those feel like things that people want or things that they're actually already doing? So we don't have an official question on that, but I would love to hear back from you. And anything else you want. In addition, we are going to ask you to start to suggest topics for future talks. And we have the next talk is already set up and planned. And right at the end, we have a little information about that.
So there are a few people who are saying in this poll that it wasn't quite technical enough. My email is on the screen right now. I'm happy to provide references to more technical content. Clearly, a lot of people thought it was at the right level, but there's always going to be people who want more detail or less detail. And I'm very, very happy to provide that additional detail on demand.
Specifically, also, you have your email. If you also can jump in, and especially those people saying they'd like to have a little more technical information, is jump into that, not the Munchie, but the more technical Slack channel for dev, and raise those questions, not just questions, raise a topic and get Ted to engage with you via that Slack. I can jump in too, but he's the better for the deep technical stuff. So I think we'll thank you, by the way, all for responding on that, and very happy to hear you thought it was a good use of your time. If we have the next Munch and Learn session is on February 4th, I'm sorry, and that is looking at the benefits of container platform and also how you can simplify and speed up machine learning development by using MLOps. The speaker is going to be Tom Phelan, and the host is Nigel Poulton. We have a survey out there. Developers love to hear back from you on that. Please notice that the survey input closes on the 8th of February. And there's a monthly newsletter. I encourage all of you to sign up for that. There's some good information and it keeps alert to things that are coming. But most importantly, please engage with the community. There is a lot of resources on the HPE development community webpage. And mainly through those Slack channels, we want the community to drive these conversations, not just have it coming from us or from the speakers. And most importantly, I thank all of you for taking time out today to join us. Please post some pictures of your munchies and make us all jealous if yours are better than my healthy little orange here. And I just wish you all the best. Ted?
I'd like to throw a plug in for Tom Phelan. He was one of the core devs on ext4, so he's definitely a file system guy too, but he has a wealth of knowledge about containers and how Kubernetes works and how this can be made easier for people to have access to. So he's quite a guy and explains things extremely well. It'll be a very good session, I'm sure.
Thanks, Ed. Thanks, Hélène. I will close the poll now, and thank everyone for participating, and hope to see you in the next Munch and Learn session. Thank you very much. Have a good rest of your day.